Yes, that's good. So I'm here to talk about spatial models, and specifically I'm talking about intrinsic auto-regressive models for areal data. And so let's look at a motivating example. This is taken from BDA. This is in BDA intended to make the point that you have events in low population counties display greater variance. So this is the pop quiz. You look at one slide first. These are the lowest kidney cancer death rates on the left and the highest kidney cancer death rates on the right. And you want to know, okay, what are these guys on the right doing that's so much better than what these guys on the left are doing? And the answer is, well, they're not really doing anything. That's just that they happen to live in counties with a very low population, and you've counted up the number of kidney cancer cases, and this is an aggregate count for an area. And so if you don't have a lot of population, you're going to see a lot more variation. And indeed, if you look at this map really closely, and you were to sort of superimpose the two of them, you'd see that a lot of these regions that have high and low are exactly next to each other. So if you put these two together, you'd start to see a map of all the areas in the United States where they're probably rural or otherwise uninhabitable. And so the intuition behind spatial models is that we want to do just a little bit of spatial smoothing, because if you could imagine these high and low counties, which are right next to each other, if you were to simply average over your neighbors, you'd probably come up with a much smoother estimate, and in fact, this spatial pattern might go away almost entirely. So for aerial data, and when I talk about aerial data, we're talking about an aggregated measure per aerial unit. So this is in contrast to point processes where you have a specific point and you have a measurement at that point and you know exactly where your point is in some geospatial coordinate system. But here you've got a polygon, and it can be as irregular as you'd like. And you do have well-defined boundaries. You have a fixed set of aerial data fixed set of aerial units, so this model is not going to help you figure out if a new county suddenly comes into your population. You're going to have to start over. And in R, we have some lovely, lovely packages that will help you plot all these beautiful maps. And you're going to be using some kind of a geospatial GIS information file. Shapefiles are what we're using here. I'm leaning on a package called SPDEP, which is going to take a description of a region and discretize it down to the set of neighbors for that region. So the data set that I've been looking at is a data set of people, mostly people, and bicyclists, not that many bicyclists, who've been hit by cars in New York City. Okay? So if you look at our data, we've got an ID. That ID is the census tract, the New York City census tract. Then the population is the number, oh, thank you. Thank you so much.
Carry on.
This is my first presentation, so anyway, so population, and that is, I'm not sure if that's the raw population or hundreds or thousands, but anyway, that's however many people live in each census tract. And then these counts are the number of fatalities. This is taken from data that came, we have a 10-year data set, and I'm just using the data from 2001. So unfortunately, there were 7 people who were hit or injured or killed by cars in the first Census Tract 2, which is in Bronx County. And you can see that we have Census Tracts 27.01, 27.02. The census tracts every 10 years, they change, the population changes, but you've got your data and it's discretized, and you're asking yourself, okay, well, you've got my geo ID there, and you've got my geo name, and these are really cool things, and these come from the shapefiles. So the challenge in working with this data is essentially munging your shapefiles, because this is a map, a representation of the census tracts, but we're not seeing the boundaries of the census tracts. We're seeing dots here that are the center, or something like it, of each census tract, which is irregularly shaped. And then we're seeing lines connecting that region with its neighbors. So for the model, the Icar model that we're going to talk about, what you care about is you care about the neighbors that are adjacent to your geospatial location, and you can define neighbor any way you want. So if we change up our metric, we'll get a much different looking picture. This is just anything that's where two borders touch, either on the edges or the corners. And this is a zoom in of a little bit of Manhattan. This here is Roosevelt Island, for those of you that know New York City. I have no idea what that little thing there is. As I said, a lot of your time is going to be spent deciding, what are my neighbors? Who really am I going to want to let into my spatial smoothing club here? So that's what we've got to work with. And the other thing that we want to talk about when we're talking about adjacency is all the ways that you can code up what is adjacency. And there are at least three ways to do it. And the way that people talk about it in the literature, which is relatively easy to visualize, is that you're going to create an n by n adjacency matrix. So in New York City, we've got about 2,100 census tracts. And if you put your census tracts, get your shapefile, and you put it through the spatial depth program and say, tell me about the neighbors, get all the neighbors for all the census tracts, what you'll find out is that most census tracts have only about 8 neighbors. So we're going to think about this 2,100 by 2,100 matrix, where on most rows, you're only going to have 8 cells that are giving you information about who the neighbor is. So the default assumption is that you're going to have some kind of adjacency encoding where things that aren't neighbors are going to be coded up as 0, and things that are going to be coded up in a way that is either binary 1, 0, or perhaps you could have anything else you want in terms of distance or weighting. But you code up the entries in your adjacency matrix. And the other way to look at a structure is as a graph, where all of your regions are the nodes in the graph, and if 2 regions are neighbors, then there's an edge between those 2 neighbors. Graph encodings, when you're dealing with a large sparse matrix, are much more efficient. And finally, then there's the R way, which is to have a list of lists that's really difficult to work with in anything other than the R packages that have coded up that list of lists. So, without further ado, the Icar model. The Icar model was introduced by Julian Bessig in 1974. He actually came up with the conditional auto-regressive model, and the intrinsic conditional auto-regressive model is an intrinsic version of the conditional auto-regressive model. So, again, we have this notion of your spatial interactions are going to be a vector of phase, and you're going to have an n by n adjacency matrix for every region, telling you who's the neighbor of that region. And then you're also going to have a diagonal matrix D, which is telling you how many neighbors each region has. And the conditional specification shows you what's going on. So here we have the conditional specification of the spatial weighting scheme, where for every phi sub I, conditional on exactly those phi's which are neighbors of phi I, you're going to have a normally distributed random variable where you have the located where you average over the phi i's of the neighbor divided by the number of neighbors, and the variance is 1 over the number of neighbors with some tau that's your variance. And so what this says is that my phi is going to be borrowing information from the values of my neighbors, and the more neighbors I have, the less variance, because now you've got more inputs to your phi I. So it's doing exactly what we suggested in looking at that map, is you're just sort of averaging over your neighbors. The joint specification, which does in fact come from, getting back to the previous talk on particle physics, was derived from looking at the positions of particles, and it's a really, really brilliant piece of reasoning to get to this joint specification. But this joint specification is in fact a multivariate Gaussian. And so we've got a multivariate Gaussian for each phi, which is centered at 0, and then the variance is described by this rather mysterious, if you're not really into matrix algebra, equation, tau times the diagonal matrix minus the weighted matrix, that the inverse of that for. And I don't have time to go into the math, but what Bessig did when he figured out the intrinsic conditional auto-regressive model was he did a bunch of math and a bunch of algebra, and he came up with this really cool pairwise difference formulation. So we can compute with that very nicely. So Bessig was interested in using Gibbs sampling to compute these Icar models, and this is really convenient for us in Stan. So for each phi, what we're going to do is we're interested in computing the squared difference, the distance between its neighbors. And we just sum that all up, and that is going to give us our spatial random variable for spatial smoothing. There is one price you have to pay for the simplification of the Icar model to get to this really, really simple expression, which, by the way, does not involve a matrix determinant and lets you compute things really quickly. You're going to have to add a sum to 0 constraint because it's non-identifiable, and you can only have an Icar prior. It's completely improper as a likelihood, but it makes a great prior. So this is a Stan program, and this is just a program fragment, really, which shows you how we code up the Icar model in Stan. And in the data block, it is assuming that we have transformed our adjacency matrix into a graph, and that we're just coming in with the number of regions, number of areal units we have, and the number of total edges in the graph. And these are undirected edges. And we represent the undirected edges in the graph using a pair of arrays where the first node 1 and node 2 are just lined up into parallel arrays so that we can use it to compute the pairwise difference. So it's a standard way of coding up a graph, and then we're going to compute our spatial random variable phi. And because we have a sum to one constraint, we have to implement it using the standard sum to one constraint as is presented in the Stan manual. So that's this. We start with our actual vector n minus of the actual phi parameter. And then in the transformed parameters, we're going to declare the phi parameter that we're actually going to be using when we do our calculations. So we have phi raw as a parameter. We have the transformed parameter phi. And what we do is we simply copy phi raw into phi for the first n minus 1 elements, and then we let the last element equal the negative of the sum of the first n minus 1 elements, and so the whole thing is going to add up to 0. And this looks pretty economical because we've used vectorized expressions to do it, and so far we're cruising along, and now we get to the final piece of the puzzle, which is in the model we can compute this likelihood, actually this prior, and we compute it by just doing target plus equals, and this is, again, dot self is just a clever way of saying multiply of squared. So we've got the difference between the vector node 1 and the difference between, but we've got sorry, I'm messing up. So we've got this vector, n-length vector phi. So we want to get to computing this pairwise difference phi I minus phi j. Those are coded up as the nodes here, node 1 and node 2. So those are all going to hold. You'll notice that we have the constraints on node 1 and node 2. Those are integer arrays that have values between 1 and n. That's because each one is just referencing that node, that phi I. So they're holding the indexes here. And so, again, we're going to be having phi at index I minus phi at index j. And we're going to have that whole quantity squared, so we use the dot self. It's really, really, really clean. It's one of the first things that people were asking for when we got the first Stan groups up. People were like, so how do you do an Icar model in Stan? And this is how you do it. And here, I don't know how well you can see this. This is taking the New York City data set and just looking at Brooklyn. So standard procedure for this model is for me to show you a map of Scotland and the incidence of lip cancer in the mid-'80s. We're going to change it up. So the top left quadrant, that's just showing you the number of accidents in each census tract in Brooklyn. And the layout here is not exactly geographically accurate, but you see that there are actually 709 census tracts in Brooklyn, and there's this particular blocky pattern. And if you tried to compute, so for this kind of account data, what you would most likely be doing is you'd be building some kind of GLM, and you would be using, for account data, you would be doing a Poisson GLM, and you would be adding the Icar component to get some spatial smoothing. So what I've done here is I have a simple Poisson model, which is the top right, And in the Poisson model, I just fit the data of population per census tract as the exposure term and or log of that, and the number of events as the count. If you have a Poisson model and there's that much variation, it can't really handle that. It's just going to give you one general city accident rate, and what you see in the top right is more or less showing you a certain amount of number of accidents in each area, but also it's being heavily smoothed by just how many people live in that area. If, on the other hand, in the bottom left quadrant, we have what happens if you just throw a regular old random effects component into your Poisson regression, it's great. You get back your data. It soaks up all the variance, and so if you think that this guy and this guy look alike, you're right, they do. They look very, very much alike. And if you're thinking that this guy, which is adding in a spatially smoothed random effect, looks pretty much like this guy and this guy, you're right, but there are differences. There are just a few differences, but they show you what happens when you do the spatial smoothing. And I've circled two regions, and you see that in both regions, for the on the left we have a model which has just an ordinary random effects component, so it's basically reflecting what the counts were for that region. And on the right we have the Poisson regression with the Icar component added in, and what you see is you do get a certain amount of spatial smoothing. So in particular, we've got two regions where the regions in the center of the circle, I'm afraid you really probably can't see them very, very well, but take my word. They're both pulled up just a little bit. They're pulled up by their neighbors, and they look a little bit more like their neighbors. So it's, I don't know, how am I doing on time?
About up.
Time's up? Good.
Why not?
Great. Okay, so conclusion. Simplified encoding is used to construct an Icar model. The Icar is improper. It can only be used as a prior. The Icar is computationally tractable for largish numbers, which is really super great. The New York City models, where I'm trying to play around with 2100 areal units, you can fit these models in an hour or two. The Icar, adding the Icar component with this strict sum to zero may give you some very weird geometries, so it's not the easiest model to fit. And coding up the pairwise difference formula is straightforward in Stan because we have vectorization, and really I'm a programmer, so I tend to come at everything from a programming angle, which is why I've really emphasized how the encodings go and how the computation goes, because at the end of the day, that's what you need to have a model that will fit in a few hours as opposed to not fitting. Thank you.
Questions?
Yeah, thank you. It's really clear Stan code. I'm not a spatial modeler, but I do think it's kind of interest in using these kinds of things for kriging or being able to smooth across arbitrary smaller units than what you have in the data and stuff like that. Do you have code out there for that condition, especially be able to get even like be able to propagate the uncertainty in the estimates into like a prediction about where that smoothing might be in between those nodes?
I'm not sure, because what we've got here, For areal units, what this model is giving you is it's giving you a Gaussian Markov random field, whereas if you've got the Kriging, that's for spatial point processes, and that goes to Gaussian processes. So they're essentially underlyingly related, but it's Gaussian processes for point data, and so either you're a point or you're a polygon. I don't know of anything in between. Yes?
But the answer was we have all the GP stuff too.
Oh, the answer is, of course, you can do everything in Stan, yes. Yes, definitely.
Rob just rewrote the chapter.
Yeah, no, for Kriging, for point processes, yes, we can do Gaussian processes. Although I think it might take a little bit longer.
Well, one question: have you compared this Earthstamp code with inla? This is package. This is an integrated nested Laplace approximation.
Sure. Yes. Dan Simpson, one of the INLA guys, was the person who helped me code this up. And INLA is faster. What's interesting is INLA does, even though it's a Laplace approximation, INLA does give you pretty much the same result. And we're working with Dan to see exactly more on that comparison, because it's a very important one. And yeah, you note I put that large-ish. The large, you're going to go to INLA. And the only reason that you would be working in Stan is that you didn't want to be crammed into the black box that is INLA. Otherwise, INLA is much, much faster.
Anyone else? Great. Thank you.